Hi everyone, in this video we'll solve the second race from the Infinity Epoch of Secureum Bootcamp. So let's get started. We have a code snippet here, and based on this code snippet we have 8 questions. So let's try to understand what the code is doing first. So this code will work on Solidity version 0.8.4. It imports reentrancy guard and possible from OpenZeppelin contract library. If you don't know what these are, you can check out my series on OpenZeppelin smart contracts. You'll find a video for each there. Moving ahead, they are creating an Insecurium DAO using the possible and reentrancy guard modules. This DAO is supposed to have an admin. This DAO is supposed to have a few members. You have an address to Boolean mapping. So basically using this, you'll check if an address is a member of the DAO or not. Then you have a UINT 256 to UINT 8 array mapping called votes. This is sort of like creating voting ballots or voting instances. So you'll have a UINT 256 voting ID mapping to a few vote options. For example, if you want to create a vote on which is better, Android or iOS, you'll create a new voting instance that will have its own ID, and you'll have some options like one for Android and two for iOS. So this is supposed to enable that functionality. Then you have a mapping of UINT 256 to UINT 8 again, storing winning outcome. So I'm guessing this is for storing the winner for each vote instance. Like taking our earlier example forward, for the vote instance where we are trying to find the better one between iOS and Android, we'll have the same voting ID here, and we'll have the corresponding winner option. Like if we had one for Android and two for iOS, and Android is favored by majority, so most likely we'll have the value 1 stored against the ID of the voting instance. Then we have a member count to keep a count of the number of members of DAO, and we have a membership fee. So after state variables, we have three modifiers. First modifier is only when open. So this DAO is supposed to be in an open or closed state, and going by this statement, which requires the balance of the DAO to be more than zero, we can say that if the balance of this DAO or this smart contract is zero, then the DAO would be closed. And if the balance is more than zero, then the DAO would be open. Second modifier, only admin, it is pretty much self explanatory. It requires the message dot sender to be the admin address. The third modifier, vote exists, takes a voting ID and it checks if the voting ID is present in vote. So basically, when you are voting for something, there would be multiple instances of voting going on. Someone is voting which one is better, Android or iOS. Someone is voting which one is better, Ethereum or Solana. So you'll have multiple voting instances going on, and each would have their own ID. So whenever someone would try to cast a vote, it would first check if that particular voting instance exists or not, and then only it would proceed forward. So this is a check for that. Then we have a constructor. It takes an admin address. It requires the admin address to be the zero address. I think this is faulty implementation here because the admin address shouldn't be a zero address, but it requires that here, and then it assigns the admin address to our state variable. Next function is OpenDAO. It's a payable function and it can only be executed by the admin. So the logic should be that admin would use this function to transfer some amount to the contract so that the DAO gets in the open state. The next function, join, seems to be for adding new members to our DAO. So it's an external function. It's a payable function because we need to pay a membership to join. It has a modifier only when open. So if the DAO is open, only then the member should be able to join, and it has a non-reentrant modifier. So reentrancy shouldn't occur while executing the logic of this function. So it requires the message dot value to be equal to membership fee, which is fair. And then it adds the sender's address to the list of members, and it stores the value true against it. Simple stuff. Then we have create vote function. So basically you are trying to create a voting instance here. You're passing a vote ID for the voting instance, and then you are passing the number of options. Sorry, the list of options. This is an external function. Modifier only when open is there. So you should be able to call it, or members should be able to call it only when the DAO is open and it is not in a pause state. It creates a new voting instance by storing the list of possible outcomes against the voting ID. And then we have a cast vote function. It takes the ID of the voting instance and it takes the option that you want to vote for or the member would want to vote for. It has a modifier vote exists, so it checks if the vote ID exists. Basically, using the vote ID, it's checking if the voting instance corresponding to that vote ID exists or not. Then there are two additional modifiers only when open, which means it should execute only when the DAO is open, and when not paused, which means it should only execute when the contract is not in pause state. Then we have a function get winning outcome, which takes in a vote ID and it returns a UINT8. So basically, if you want to see the result of a voting instance, you pass in the ID corresponding to that voting instance and it would return the winning option for that voting instance. Then we have a function to set the membership fee. It takes in the fee amount. It is external and can be only executed by the admin, and it sets the fee amount as the membership fee. The last function, remove all members, is again external and should be only executed by the admin. It deletes the caller's account from the list of members. So I think this is going to be a bug because the function is remove all members, but it's just removing the caller's address from the list of members. So that was the contract. Let's start solving questions. The first question, based on the comments and code shown in Secureum DAO, option A, DAO is meant to be opened only by admin by making an Ether deposit to the contract. Yes, there's a function called OpenDAO which is external, payable, and should only be accessed by the admin. So this is true. DAO can be opened by anyone by making an Ether deposit to the contract. Yes. So the intended logic here is that only admin should make a payment to the DAO and open it, but anybody else can make a payment to the DAO. We don't have any fallback or receive function here. So in case any account makes a simple Ether transfer, most likely that would go through and the balance of the contract would increase. Also, apart from that, you'll see in the solution that you can also force send Ether into this contract via self-destruct. So you create another smart contract with some balance and you call self-destruct on that contract. And in the self-destruct, you need to specify an address where you should send the balance of that contract. So you can specify the address of this contract while self-destructing the other contract. And that's how you force send Ether into this contract. So yes, B is also true. Although DAO is meant to be opened only by the admin, it can be opened by anyone. C, DAO requires an exact payment of membership fee to join the DAO. Yes, we have this function join where it checks if the message dot value is equal to the membership fee or not. So this is also true. And since ABC are true, D is false. The second question, based on the comments and the code shown in Secureum DAO snippet, a guarded launch via circuit breakers has been implemented correctly for all state modifying functions. So for this, you need to understand what circuit breakers are, and there's this documentation by consensus according to which circuit breakers stop execution if certain conditions are met and can be useful when new errors are discovered. For example, most actions may be suspended in a contract if a bug is discovered and the only action now active is a withdrawal. So if you understand what possible module does, it is basically this. So coming back to the question, guarded launch via circuit breakers has been implemented correctly for all state modifying functions. So if I were to simplify the wording of this option, by my understanding, it's trying to say that wherever we have a state modifying function, all of the checks there have been implemented correctly or not. So we have a few issues here as we discussed in the first question. The function OpenDAO has the only admin modifier so that only the admin address can access this function. But the functionality that only admin should be able to open the DAO doesn't really hold well because anybody can send Ether via some other means, and those cases are not handled properly. There's one other example that it's not checking if the person creating the vote or the person casting the vote is a member of the DAO or not. So again, these are state modifying functions, but necessary checks are not there in place. So this is false. B, zero address checks have been implemented correctly. So while explaining the contract, I already covered this. In the constructor where you are assigning the admin to this DAO, there's a require statement that checks if the admin address is a zero address or not. Now, this is logically false because the admin address should be an operatable address, not a zero address. So, this is also false. All critical privilege role functions have events emitted. We didn't find a single event being emitted in this contract. So, this is also false. So, since everything is false, D is true. The third question, reentrancy protection only on join, assuming it's correctly specified, indicates that A. Only payable functions require this protection because of handling message.value. So we'll see the join function and we have a non-reentrant modifier here. So basically we are protecting this function from reentrancy. The question tells us that we should assume that the reentrancy protection is correctly specified. So that means that there are chances for reentrancy to happen in the join function. Now the option A, only payable functions require this protection because of handling message.value. So tying this with reentrancy, you don't need reentrancy protection to protect the payable functions that are handling message.value. So for example, if someone is sending ether into your contract, you don't need to protect your contract from reentrancy in that case. You only need to protect your contract from reentrancy when you are making external calls to untrusted sources, and especially if you are sending ether to those contracts. So those are the cases in which reentrancy can occur, and reentrancy protection is applied to prevent that. So the first option is false, and the option B, join likely makes untrusted external calls, but not the other contract functions. So since we are assuming that reentrancy protection is applied correctly, most likely join would make external calls to untrusted contracts. So B is true. Both A and B, this would be false because A is false. Neither A or B, this is also false because B is true. Fourth question, access control on message.sender for DAO membership is required in create vote to prevent non-members from creating votes, cast vote to prevent non-members from casting votes, and get winning outcome to prevent non-members from viewing winning outcomes. Now, if we go back to the code above, we don't see any access control for prohibiting anybody who is not a member of the DAO from executing these functions. So logically, it's pointless to be a member of the DAO because you can access these functions anyways. So you would need an access control checking whether you are a member of the DAO or not on create vote. You would also need it on cast vote, and you shouldn't really need it on get winning outcome because anybody should be able to view the outcome of the vote. It's just that the members of the DAO should be able to create and cast their votes. So coming to our question, create vote to prevent non-members from creating votes, true. Cast vote to prevent non-members from casting vote, true. Get winning outcome to prevent non-members from viewing winning outcomes, false, because the outcomes of the voting should be available to anyone. And D would also be false. Fifth question, a commit reveal scheme, which is a cryptographic primitive that allows one to commit to a chosen value while keeping it hidden from others, with the ability to reveal the committed value later, is relevant for, and then we have the options. So, to simplify what is a commit reveal scheme, you are basically in this context you are committing to something, let's say a vote, you are casting a vote, but you don't want to disclose what option you have chosen for in the voting instance. You only want to disclose it once the voting round has ended, and then only others should be able to view the option that you have chosen. This is done for the fairness of elections. Like whenever an election happens, you don't really reveal who is voting for who because that, in a way, dismisses the entire point of having the voting. So that is what is meant by a commit reveal scheme. Now we'll go through the options. A, join to not disclose message dot sender while joining the DAO. So in simple terms, we would like to hide the address of the members that are joining the DAO. There's no point in hiding the address of the members. So this is false. Then create vote to not disclose the possible outcomes during creation. So again, in simple terms, this is when we are creating a voting instance with a voting ID and the possible outcome options. Do we want to hide the possible outcomes? No. We want them to be visible so that other people can vote on them. So this is also false. Cast vote to not disclose the vote being cast. This is true. We want to hide the vote option we are choosing until the voting ends. So this is true. And since C is true, D is false. The sixth question, security concerns from missing input validations is are present in create vote for duplicate vote ID. So we'll go to create vote, and in create vote we are creating a new voting instance. So we are not checking if the vote ID using which we are creating a new voting instance already exists in our set of voting instances. So this could overwrite a previous voting instance. So option A is true. Cast vote for existing vote ID. So we have a modifier vote exist which takes in the voting ID or the ID of the vote instance and checks if a voting instance exists against that vote ID. So cast vote does have a check for existing vote ID. So this is false. Get winning outcome for existing vote ID. Now get winning outcome doesn't have this modifier vote exists, but again you are not doing any kind of state changes here. You are simply reading the smart contract data. So if a vote ID exists, which means there's a voting instance and you will get the result of that voting instance. If the vote ID doesn't exist in our set of voting instances, you would get 0 as a return. So this is not really problematic. So C is also false, and then set membership fee for sanity threshold checks on fee. So if we see a set membership fee, this function is working fine. Only admin would be able to call it and update the membership fee. But there's a logical flaw here. We have a membership fee of 1000 at the moment, but admin can basically set the fee to a very high amount, preventing anybody else from joining the DAO. So there's a logical flaw here, and there should be some kind of check. There should be some kind of range for the membership fee, like between 500 and 5,000 or 500 and 10,000, so that the admin cannot set an arbitrarily large fee and prevent anybody else from becoming a member of the DAO. So D is also true. The seventh question, remove all members function will not work as expected to remove all the members from the DAO. So I've already covered this in my contract explanation. Remove all members by its name should ideally remove all the members from the DAO, but it only deletes the address of the person calling this function, and that person would only be the admin of the contract because of this modifier. So remove all members by its logic deletes the admin's address from the list of members of the DAO. So A is true and will work as expected to remove all the members from DAO. This is false. Is a critical function missing an event emission? Yes, we don't have any event emitted after removing the member. So C is true, and since A and C are true, D would be false. Next and the last question of this race, question number 8. In Secureum DAO will not be susceptible to something like the 2016 DAO exploit. Option A, because it derives from reentrancy guard, which protects all contract functions by default. So this is false because we know that reentrancy guard is only there on a single function. So this is false. Only if does not have a withdraw ether function vulnerable to reentrancy and makes no external calls. So we didn't find any such function in the smart contract we have. So only if that kind of function is not there in the complete smart contract, we would escape from something like a DAO exploit. So this is true. Option C, because Ethereum protocol was fixed after the DAO exploit to prevent such exploits. This is false because fixing Ethereum protocol doesn't save this particular smart contract from a reentrancy attack or any exploit. Protocol is a different thing, and a smart contract running on top of that protocol is a different thing. Because Solidity language was fixed after the DAO exploit to prevent such exploits. This is again false because it doesn't matter if the Solidity language was fixed or not. If you have a security flaw in your smart contract, a logical security flaw, it will get exploited anyways. Fixes in the Solidity language won't help you with that. So, with that, we have completed this race. I hope you have learned something. Check out the videos on other races. Comment your doubts or leave a feedback. Like, share, and subscribe. Thanks for watching, and I'll catch you in the next.